What's good, Code Milkers? We're on the 30-day Elite Coding Challenge. Let's check out day... What day are we on? 11. Diameter of binary tree. Okay, this is a problem that I actually looked at before. Not now, but like probably a month ago. I looked and I took one look and I thought, I don't feel like doing this. This one looks kind of hard. So I'm going to do it now. Given a binary tree, you need to compute the length of the diameter of the tree. The diameter of a binary tree is the length of the longest path between any two nodes in a tree. It's a problem. Compute the length of the diameter of a binary tree. Diameter is the length of the longest path between any two nodes in the tree. This path doesn't need to pass through root node. Okay, let's take a look at the example they gave us. 1, 2, 3, 4, 5, with the 1 being the root, 2 being the left node of that root, and 3 being the right node. And then there's a couple nodes branching off of the 2 node. And this returns 3, which is the length of the path from 4, 2, 1, 3, so 4, 2, 1 to 3, or 5, 2, 1 to 3. So in this case, it does pass through the root, but there could be an example where it passes through the 2 node. For instance, if we had like 2 left nodes going off of the left 4 node, like if we had a left and then off of that left node another left, that would be 1, 2, 3, 4 to that 5. So 5 to 2 to 4 to that one's left, and then to that one's left. And that would be the longest diameter in the tree. So their example, it makes sense. Passes through root and is the number of edges. So edges meaning the actual lines, not the number of nodes, but the lines between the nodes. So there's 1, 2, 3. Some people define that as the height of the tree, the length from the root to, well, the number of edges, so lines from the root to the deepest node in the tree. So wherever the leaf node is farthest down, that could be the height. For this, I'm not sure if we're counting as height, but so we'll count the edges. So we want to keep track of the edges, not the number of nodes. Okay, number of edges, 3. Data structures, obviously we have a binary tree. For problems where we need to go deep into the tree, it's best to use a depth first search. So we want to go all the way down the tree first and then work our way recursively back up to the root node. So in this instance, with the 1, 2, 3, 4, 5 tree, we would call root left, and then we get to 2, and then we call root left, and then we get to this 4, and we call root left, and it's null. So then we do our subproblem on the 4 node, and we check its, we also check that we would also call the recursive function for the right node of it, and since that's null, it would stop there also. We compute the subproblem at 4, then we would go to 5, and compute that subproblem because it is connected to leaf nodes, meaning that there's no node there, it's just blank, it's null. Compute the subproblem there, then we go back up to 2, compute that one subproblem, Then we go over to 3, compute that subproblem, and then we get back up to the root and compute it there. And whatever one has the highest diameter from that root, like from the height of the left side and the height of the right side to the root, whichever one has the highest left plus right height is the diameter for the whole tree. So we want to do recursion because it's depth first search. I forget what kind of traversal it is since it's since we're going left, right, and then to the calling node. That might be post order. Let me check it up. Post order traversal. Let's see. I don't want to click on one of these, and it might have the answer. I don't want to like look at it. So post orders left, right, and then node. Yeah. So we're doing a post order recursion here. X is kind of hard to click. Okay, there we go. So we got the recursion with depth first search, post order traversal. And let's start thinking about this algorithm. Bless you.
Thank you.
The algorithm, we would start at the root. Well, that's the recursive function. We want to think broader than that. We need to declare diameter as variable and assign it 0. 0 is going to be returned if we have a root that is just null, because there is no diameter, so it's 0. Then, so long as the root is not null and has, at least one child node, it should be 1. Should be at least 1. So it's only going to be 0 if the root is null or if the root node has no left or right children. Declare diameter as variable, assign it to 0. Then we need to create a recursive function for post order traversal. Then now let's go inside this recursive function. So the problem essentially is we are keeping track of the diameter as we go through the tree. And for each node, we want to traverse to its left and right. And we want to figure out the height of each left and right node. And then figure out the diameter between the two. So it's left plus right. Because like we saw in this example here, of the root node, the left node's height is 1, 2, and the right node is 1. Like the longest path is 2, the longest path here is 1. So I want to figure out the longest path for each side, and then add them together, and that's our diameter. So we need to, in the order, we need to first check if null, return 0. Now, if it isn't null, then we can traverse to its left and right children. So we need to do recurse to node.left, recurse to node.right, and we want to store the result in left var, store result in right var. Now we want to compute the diameter. So, well, we need this recursive function to return something other than 0. So, like right now, it'll only return 0, which will make the diameter always 0. So we need to return, I guess, the number of edges we're at, like the current number of edges we're at from the root node. So once, like, let's take for example the 1, 2, 3, 4, 5. If we went down to the 2 node, so we went one level deep, we added one edge, so we can do 1 plus. Yeah, we can just do +1. So we could return 1 there. And then if we are going down to the 4, we would return 2 because we are one more level deep. So with each level, we want to return 1 plus. I guess 1 plus. It's 1 plus the current level of left or right. So I'll write down here, return 1, return +1, incrementing for each recursive call. And then before that, we also need to reassign diameter to the max of, let's see, either diameter or left plus right. Because we've seen the diameter is the height of the left plus the height of the right through the current node. So for the, let's see if I can predict the values here. We'll go on the post order traversal. The 4 node has 2 null nodes as its children. So that would be 0 plus 0, which will leave our diameter at 0 because that's not greater than 0. 5 would be the same because it has 2 leaf nodes. Well, 5 is a leaf node because that's where it ends, but it has null nodes on it. So 0 plus 0 is 0. Then we go up to the node 2, and it has a left height of 1 and a right height of 1. So we do 1 plus 1 because the height of both sides summed, and that gives us 2. So the diameter is now 2. Now we go over to 3, and this is just like what we saw with the 4 and 5 leaf nodes. It doesn't have any child nodes, so it is just 0 plus 0, which is 0, and leaves our diameter at 2. Then we go up to the root node, and we have the left height of it is 2, and the right height of it is 1, because the longest number of edges on the right side is 1, the longest number of edges on the left side is 2, which summed gives us 3, which is our new diameter. So really it seems like return +1. We need to really return 1 plus the max of either left or right, because it just feels right. I'm not sure how to explain it. I'll come back to that. So that's the end of that recursive function. Here we return diameter. Okay, let's try coding this out. Let diameter equal 0. Function expression. Here we'll call it DFS for depth first search. It takes a node. We return the diameter. And if node is null, we just return 0. And that would be, for instance, in our case of 4, we would traverse to the left of it, which would be null, return 0. And then for 5, and then for the right side of 4, we would return 0. So the height of each of its child nodes would be 0. That's the number of edges. So 0 plus 0 would be 0. Then we want to declare left, which is recursive to node.left. Then right is DFS node.right. Now, this recursive function is a little messy in that it has side effects, so the diameter variable is actually outside of it. For this question, it works. I wouldn't recommend it overall, but in a pinch, the side effect probably is going to work well. Diameter is the max of either the current diameter, which will leave it the same, or left plus right. And then we want to return 1 plus turn 1 plus math.max of left or right, whichever one is bigger, because that is the number of edges that we're currently at. So like if we went to the 2 node, we would have been returned, like let's just follow this through all the way, like starting from the beginning. So starting from the beginning, we do left, which is DFS on node.left, which takes us to the 2 node. Then, since we're recursing, we are calling DFS again, which first does DFS node left, which takes us to 4. Then it takes us to the left node of 4, which is null, which returns 0. And now we're back here at 4. And now we do the right side, DFS node.right. Since that is null, we go back up to 4. And then we compute the diameter, which is the max between diameter or left plus right. 0 plus 0 is 0, so we don't change the diameter there. Then we return 1 plus the max of either left or right. So in this case, they're both the same, so it doesn't matter. But it's going to return 1, because 1 plus 0 is 1, which means we have, which means that left in the subproblem at 2 equals 1 now, because we have one edge between 2 and 4. Now we go to right now from the second node. We go down to 5, and we do left, which gives us 0, and we do right, which gives us 0. Then we go back up to 5, and it's just like with 4, 0 plus 0 is 0. And then we return 1 plus 0 is 1, and we go back up to 2. And there we do 1. We do the max of either the current diameter or left plus right. Now left plus right is 2, which gives us a diameter of 2. Now we're back up to the root node, and now we're going to compute the DFS of node.right, which will take us to 3. Then we're going to do left and right, which both are 0 because they're null. So 0 plus 0 for 3 is 0, leave the diameter at 2. Then we go back up to 1, and we compute, and 3 returned 1, because 0 plus 1 is 1, and 2 returned, the left call of 1 returned 2, and the right call of 1 called 1, and we return 1. Because the 2 here returned 2. It returned 1 plus the max of either left or right, and the max was 1, so 1 plus 1 is 2, which gives us the number of edges from 1 down to either 4 or 5. And then from there we have 2 and 1, respectively, for left and right nodes, for the height of each. And then we do diameter is equal to the max of either the current diameter, 2, or left plus right, which is 3. Gives us 3. And there, since we're done traversing, we return the diameter, which is going to be 3. that was a lot to work through the subproblems. I'm not sure if this is going to work. It works in my head, so we'll see if it works in the interpreter. It's taken a little bit. Your answer is 0. I wonder why it gave us 0. Oh, because I never invoked DFS. We're doing that from the root. Let's see if that works now. Okay, gave us 3. Good. We've talked about edge cases. Let's give a empty one, and we'll give it 1. Great. So it catches the 2 edge cases that I've thought of. And 1, 2, 3, 4, 5. Let's try it out. Please work. I don't know how to refactor this if I don't. Yes! It worked. Thank goodness. This is probably the hardest problem yet for me on this, I would say. Just because recursion is not my strongest skill. But it worked. That's all that matters. So thank you for watching. Have a great day.